Okay, so welcome everybody to the IMSc Algebraic Combinatoric Seminar. It's really a great pleasure today to have Sheila Sundaram, and she's going to talk about plethystic inversion and representations of the symmetric group. So Sheila, please.
Thank you. Thank you very much for the invitation. Yeah, so there's the title of my talk. Let's see. So I'm just going to go through some background and please, stop. It's useful to have both points of view in mind whenever you see any sort of formula with symmetric functions. So plethism, if you talk about GLN characters, then the easy way to describe it is as composition of just function composition. So that's why I'm writing F square brackets G. I think McDonald uses a little circle. So this just means like F little o G, right? For the symmetric group, what we're really doing is working with wreath products. So you're taking a representation of Sm, wreath product Sn, and inducing that. So again, so my notation, I'm trying to be consistent here. Wreath products, people often write as the Sn outside with the little twiddle and the Sm. So this, just to make it clear, this has order n factorial to the power m times m factorial. All right. And let's see. Partitions. So, okay. So I think, I'm sure everybody's familiar with this, but my partitions will be weakly decreasing, k tuples here, and L of lambda, that's k, that's the number of parts of lambda. These are integer partitions again. PR is the R's power sum symmetric function. So it's the sum of xi to the r, right? And then p lambda is just, you're just extending the PRs multiplicatively. So for every partition lambda, there's a power sum p lambda. S lambda is the famous short function indexed by the partition lambda. So what is p lambda? So again, as I said, I like to think about these things in terms of the actual representation. So up to a scalar multiple, p lambda is the Frobenius characteristic, which I know I haven't defined, but it's basically, you should think of it as the class function that's 1 on the conjugacy class indexed by lambda and 0 everywhere else. Right? The scalar multiple is the order of the centralizer. Okay. S lambda corresponds to the irreducible for the symmetric group indexed by lambda. Okay, and one last thing which I might sometimes say is when is a symmetric function Schur positive? So we're interested in that because Schur positive means it's a non-negative combination of Schur functions. So that means it corresponds to a true Sn module. Okay, so one of the things that's going to show up a lot is...
Can I ask you a question on
yes.
the very first slide, please?
I'm sorry?
On the very first slide.
Yes.
If we could go back, please. One more.
Yes. That one?
No, one more, please.
One more back?
Yeah.
Seems to be stuck. Okay. This,
and then you said something about wreath product.
Oh, yeah, I did. Yes, that one.
So, so SMSN is, how is this? So I thought wreath product meant taking n copies of SM and then acting SM.
Yeah, this is, I'm sure this is hard to hear over the Zoom. So the outside one is the number of copies, right? Mm-hmm. So the map, the correspondence here is F. You should think of the F as coding for a character of the outside factor, and G as coding for the inside factor. This is the normalizer of M direct. Oh, I can write. Sorry, I forgot. Let me write it. Let's see. Okay. So this. Okay. So this thing, let's see, is the normalizer of Sn cross Sn cross Sn m times.
Ah,
Okay, does that make it better?
Yeah.
Is it okay?
So one second. So how was, sorry, so Sn cross M times, and then you act Sm by permuting these copies, right?
So if you have a representation of Sn, so you would take its tensor product, its n-fold tensor product,
Yeah.
and then you would also take a sort of, all right, this is going to get kind of in the weeds here. And then you would take the representation of Sm and tensor with that, and there's a specific way to act that I guess I don't really want to go into.
Okay, fine, no problem. Thank you.
But I'm happy to show you afterwards.
Okay, sure.
Okay. All right, so let's see, I have to go back. I know it tells me the page number, but I wasn't keeping track, so. Okay, so is that where I was? Right. I think this will become, your question might become clearer as I go on. All right, so the homogeneous symmetric function, Hn, degree n. So that corresponds to the trivial representation of Sn, right? And it's also the character of GLV acting on this nth symmetric power of V, right? So those are the two ways of thinking of it. Similarly, for the elementary symmetric function, right? It corresponds to the sign representation. And it's also the GLV character acting on the nth exterior power. Okay, the involution omega, that's going to show up a lot also, is just in the ring of symmetric functions, you're sending Hn to En, right? So, okay, so this involution then in the ring of symmetric, for symmetric functions, for the symmetric group, it corresponds to tensoring with the sign representation. And for GLN, it doesn't really have any kind of nice description like that other than you're transposing the shape, right? And then finally, P1 to the N, which is, by the way, same thing as H1 to the N, or E1 to the N. That's the Frobenius characteristic of the regular representation of Sn. So an underlying current in this talk will be different ways to decompose the regular representation and why they may or may not be interesting. Okay. Oh, so P1 to the N also for GLV, it's the character of GLV acting on the nth tensor power of V. Let's see, so, yeah. Okay, so this slide is mostly just to fix notation again. So I'm going to be looking at two series of symmetric functions. I'm going to add all the homogeneous symmetric functions, but I do want to add one. So H0 is 1, and the same thing for E. Right? And so if I take a symmetric function that looks like this, where F1 has, you should think of F1 as having degree 1 and so on, then I want to think of it as a character of this, a GLV character of this direct sum. And then when I do when I write H plethism with F, this is now in the ring, I'm in the ring of symmetric functions. This is the GLV character of the symmetric algebra of W. And similarly, E of F is the GLV character of the exterior algebra of W. And more specifically, if lambda is the partition with mi parts equal to I, I'm going to write H subscript lambda of F for the character, the GLV character on this piece. So I'm taking mi symmetric power of Wi and tensoring all those together. The same thing for E lambda of F. Okay. And then finally, if you just invert 1 minus P1 in the ring of symmetric functions, so of course you're just getting the sum of P1 to the n, that's a GLV character on the full tensor algebra. Okay. Okay, so now if you're in the symmetric group, however, so this really depends on your preference, it's a little more involved because you have to talk about Rees products, and Rees products are messy. But you get used to it. Okay, so what's H lambda of F? In the ring of symmetric functions, you can take it apart and it's just a product over I of the single homogeneous symmetric function HMI plethism with Fi. That's how you would actually compute it, right? So I'm thinking of Fi here as homogeneous of degree I, right? And what it really is the Frobenius characteristic of this induced module. So the modules are induced from this subgroup. So it's a direct product of SMI Rees product SI. So it's the normalizer in Sn of this huge direct product of Mi copies of Si again. Right? So everything is being induced from this normalizer. Okay, the regular representation, right? So this, I think everybody is familiar with, how the regular representation decomposes, right? It's the sum over all the irreducibles with chi, with dimension chi copies of each irreducible chi. So for the symmetric group, there's this, famous fact that combinatorialists have exploited to the hilt, how the regular representation decomposes. It's a sum over partitions lambda of n, f lambda times chi lambda. And f lambda is the number of standard Young tableau shaped lambda. And the little s lambda here is the Schur function indexed by lambdas. Right? So this is my, I'm calling this my 0th decomposition. Okay. I actually want to talk about a different one because all my plethisms are going in this talk are essentially going to come from here. So I'm going to take the cyclic group generated by the long cycle, 1, 2, up to n. And I'm going to let omega n be a primitive nth root of unity. So this is just a cyclic group, it's abelian. So all the irreducible characters are basically the n distinct powers of omega n. Right? So if I write the regular representation, these are all linear characters. So the regular representation is, you can write it as just the sum of these n characters. But whenever you do something like that, actually with any subgroup, you immediately get a decomposition of the big group, a regular representation of the big group. So here it is, just by inducing up, right? The regular representation of Sn decomposes into a sum of induced modules, and every summand is induced from the cyclic subgroup. A one-dimensional character induced from the cyclic subgroup. So that's, okay. So the proof is very simple. You just start with a regular representation of Cn and induce it up, right? Okay. So what I want to talk about is, and this has been, the literature on this is huge, the actual summands in this decomposition. So the two ones that I want to single out right now are what I'm calling V subscript n, which is when you take just the primitive root, and conj subscript n, when you take the primitive root to the power n. So in that case, you're just taking the trivial representation on the cyclic root. So the first one is a faithful representation, and the second one most certainly is not, right? Okay, they're both interesting. So this, I am going to say more about the first one, but let me just point out the second one is just, okay, so this is just a permutation module. You're acting trivially on the uncycles. So the stabilizer is the cyclic root. So that means this is exactly the conjugation representation on the class of n cycles. Okay. Right. Ramanujan sums. All right. So, sorry, are there any questions up to this point? Okay. So, mu of n and phi of n are the numbers theoretic Möbius and totient functions, right? So phi of n is the number of integers less than n and relatively prime to n. And mu of n is the Möbius function actually in the divisor lattice. Okay. I'm going to let Ln superscript k denote the Frobenius characteristic of this representation. So it's the kth power of the primitive root induced up from the cyclic root. Okay. So it's a theorem of Folk's that, well, I think I read somewhere that, I mean, there are other people who've done this calculation. So he figured out what the Frobenius characteristic was of this representation. So you get this sum. This is PD, the d's power sum to the power n over d. So what is this saying in terms of representations? It's basically saying that the character is supported on, this induced character is supported on permutations whose disjoint cycle decomposition has all cycles of equal lengths, right? And that's, if you just use the formula for the induced character, that's immediately obvious. That's going to happen anytime you induce from the long cycle. Okay, so this thing in blue is what is called a Ramanujan sum. I don't know anything about the history of it. That's what it seems to be called. I do know that it's quite old. It goes back to von Sterneck and Holder, but the things I know about it are from the book by Hardy and Wright. So that's pretty old too. It equals, so what is it? It's the sum of the kth powers of all primitive dth roots of unity, right? So if you work that out, it's, you know, kind of an intricate calculation if you're doing it for the first time, but it comes out to be this. Okay. So I just wanted to point this out because so when I'm going to be doing plethystic computations with this symmetric function as the inner factor, and you can immediately see that if you did this brute force, it's going to get very messy. Okay. All right. So I sort of switched notation on you. So I just wanted to point out that Ln superscript 1 was Li n and Ln superscript n was conj n. So in those two cases, that formula, Folk's formula, simplifies considerably. And you have this thing that's very familiar to a lot of people, I'm sure. The Frobenius characteristic of Li n is this very simple linear combination of power sums, PD to the power n over d, and the coefficient is the Möbius number. And then for the conjugacy action, this is possibly less simple, less familiar. The Möbius number is replaced by the totient function, Euler's phi function. Okay. So if you know about the combinatorics of necklaces and primitive necklaces and things like that, I mean, just this is the formula that gives you those counting facts. Okay. Let's see. All right, and there was just one more connection that I wanted to mention. The ring of coinvariants. This is like a current, well, generalizations of this are current hot topic in algebraic combinatorics. So I just thought I would mention the connection here. I want to take the polynomial ring in n variables, and I want to mod out by the ideal generated by the non-constant symmetric polynomials. Okay? That's called the coinvariant, the ring of coinvariants for the symmetric group Sn, and it carries a representation of Sn. If you took the symmetric polynomials, just the symmetric polynomials, that would be the ring of invariants. Right? Okay, so it's an old theorem of Chevalier, who did much more than prove this. I think he did it for all finite reflection groups or something like that. This is all, you can find this in Humphrey's book on reflection groups and Coxeter groups. Right? So the ring of coinvariants affords the regular representation of Sn. Okay, there's obviously a natural grading on this thing just by degree of the polynomial. So it's interesting to think about what those graded pieces are. Okay. So this is a theorem of Krusky, Rich, and Raymond. And there's seems to be a long and interesting history of why the manuscript was circulating back in 1987, I think, but it took a long time to get published. Anyway, one of the things they proved is that if you take the graded components and add them up by degree congruent to K mod n, then that sum is precisely isomorphic to this induced module. It's kind of an amazing theorem, I think. So the next question is, I guess.
Can I ask you a question here?
Yes.
This is a question about the literature. I vaguely remember there is a conjecture of Procesi proved by somebody in the advances, maybe in the 90s, on what the decomposition of Ri is.
Yes. I used to know
to this,
at one point in the 90s, but I don't remember the details anymore. There was a lot of discussion about this back then. Yeah.
So this may not be related to that. Would you know this Weimann-Kraiskevich theorem?
May not be. No, I think it is actually related. You'd have to, but I don't know the details. I'm sorry, I'm having a little trouble hearing you. So
oh, sorry. Maybe I should speak up louder. Sorry about that. No, that's fine. It's just a vague question anyway. Thank you.
Okay. Okay. So the question of decomposing this into irreducibles is now a famous theorem in algebraic combinatorics, right? Oh, so I should mention Richard Stanley's EC2 enumerative combinatorics is a great place to look for comments and history and things like that, and more references. Okay, so the theorem is that the multiplicity of the irreducible chi lambda in this induced module from the long cycle is the number of standard Young tableau of shape lambda whose major index is congruent to K mod n. So I didn't write anything down. Oh, sorry. Okay, so what does this mean? So standard Young tableau, let's see. I'm going to try and draw one. Yeah, okay. So I'm going to draw, let's see. So I'm going to draw a Ferris diagram this way, right? This is the Ferris diagram corresponding to the partition 3, 2, 2 of 8, oops, sorry, I wanted to make it 3, 3, 2. I had a reason for doing that. Okay, so a standard Young tableau of this shape is simply a way to fill the boxes with the integers from, in this case, 1 to 8, so that they're strictly increasing left to right and strictly increasing top to bottom. So let's see, I'm going to try this. 2, 2, 3, maybe I'll do that. Oh, I'm missing a box, aren't I?
Third row.
Yeah, I'm missing a box. Okay, let's see. 3, yeah, right. Whoops, sorry. 7 and 8. Okay. Let me fill my box. There we go. That's what I wanted to do. Okay, so first row is 1, 2, 6. The second row is 3, 5, 8. And the third row is 4, 7. Right? So that's a standard Young tableau of this shape. So I have to tell you what major index is. So major index is the sum of the descents. So I have to tell you what a descent is. So a descent, I'm going to circle them, is any integer I, so that I plus 1 appears in a lower row than I. Right? So in this case, 1 is not a descent because 2 is not lower than 1, but 2 is a descent because 3 is lower. 3 is a descent because 4 is lower. 4 is not a descent because 5 is above it. And 5 isn't a descent because 6 is above it, but 6 is a descent because 7 is below it. Okay? Okay, so the major index for this particular example is 2 plus 3 plus 6. Right? So that's 11, right? And 11 is congruent to 3 mod 8. Okay, so what that's telling you is that this contributes 1 copy of the irreducible index by 332 in the decomposition of this representation. So if you've never seen this before, I'm happy to go over it again. Are there any questions about this? This isn't going to come up much, but it's interesting, so I just wanted to mention it. Right? So what we're looking at is the notion of descents, and you're adding up. So major index is the sum of over all I, such that I plus 1 is lower than I in the tableau T. Right? So that's what I did. Okay. All right, so this is really a remarkable theorem, I think. This thing, there we go. It goes away, but it takes its time. All right, so.
So can I ask you a question, Sheila?
Yes, sure.
Could you just go back to the previous slide?
Yeah.
So is it also true that the multiplicity of chi lambda in that grade Ri would actually be the number of standard tableau whose major index is equal to I?
No. You have to take it mod n. That's very important.
I see. Okay.
Yeah.
But is that other number known? I mean, do we know precisely the decomposition of each grade of the Ri?
So what you're doing is you're taking all the degrees that are congruent to k mod n,
Yeah.
And then you're finding the irreducible decomposition of that and that. So when you take all the degrees congruent to K mod n, you get precisely this induced module. It's not telling you anything about the individual graded pieces.
Okay. Okay. Thanks.
Okay. Let's see. So I'm going to write, that is right, yes. So I'm going to write just Lie without a subscript for this symmetric function, which it's really a formal power series here. I'm adding up all the Lie n's, right? So Lie n, if you remember, was just, I'm just taking the primitive nth root and inducing up from the long cycle. So it's, again, an old theorem of Thrall that if you take H outside, do the Plethysm with Lie, you get 1 minus P1 to the minus 1. So in other words, you get, your nose is painful. So you're getting, oops, this is 1 plus P1 plus P1 squared, and so on. Okay. So you can prove this. So if you just, if I have time, I did want to do this at the end, right? So, okay. Okay, so, but let's look at this for a second. So remember I said P1 to the power I, that's the character of GLV on the ith tensor power, right? So this is giving you a decomposition of the tensor algebra. That's what I wanted to point out. Or in terms of the symmetric group, it's giving you a decomposition of the regular representation of the symmetric group. So I believe I wrote that in my next slide. So this plethystic identity should really be read like this in terms of representations. And that is actually what Thrall proved, right? He proved that the regular representation of Sn decomposes into a sum of pieces indexed by partitions lambda of n, and each piece looks like something basically induced from a product of Reith products. But because, so this is a sum of modules induced from normalizers, but because each of the inner pieces, the Lies, are themselves induced from cyclic groups, you can actually think of them as modules induced from centralizers. So if you take MI Reith product CI, where the inner factor is now a cyclic group, you're actually looking at the centralizer of an element of that type. Okay, so plethystic inverses, I'm going to say F and G are inverses if when you compose F with G or G with F, you get P1. Because plethism is associative, these two things are equivalent. Right? You're in the plethism ring, basically. So this is the business about if you have a left inverse, you have to have a right inverse, and they have to be the same, right? Okay, and then the important theorem here is if you have a symmetric function with no constant term, that's very important, and non-zero coefficient for P1, then F has a plethystic inverse. I wrote proof here. This is really an idea of the proof that you can sort of get started on computing, right? So I should say proof. This is the idea, right? Okay, so what you're doing is you're writing, you break up F into its pieces, summands of homogeneous degree, and then write P1 equals F of G, and use the fact that plethism is linear in the outside variable. And then if you start isolating by degree, you can, in theory, recursively compute the homogeneous pieces of G. I say you can in theory. In practice, this is hard to do. Okay. Sorry, can you at least tell me if something is blocked here? Because I don't, I'm trying to look at two screens at once. Okay. All right, so some examples. P1 minus 1 and P1 plus 1 are inverses. Now, I know I just said you have to have no constant term, but I wanted to include this one because this is a very important pathological exception, right? Let's see, P1 over 1 plus 1, P1, and P1 over 1 minus P1 are inverses. This is easy to check just by actually physically computing the plethism, right? So the PI's PM plethism PK is just PMK, right? So these are all P1s, so it's very easy to compute. And then this one is slightly less trivial. I wanted to include this because you can play around with it. It shows you what's going on with the Möbius function. So when you take the plethism of these two things, you are going to be doing exactly Möbius inversion in the divisor lattice. So that's what it amounts to. So that's why when you do the plethism, you get P1, right? So I tried to pick examples where it might, be instructive to do them out. Okay. All right, so probably the example of Plethystic inverse par excellence is Cadogan's theorem. This is a 1971 graph theory paper that I think I've looked at, but never really gone through the details of the proof because there are much nicer ways of, well, for me, of proving this, right, than whatever he did with graph theory and cycle indicators. The Plethystic inverse of H minus 1. So remember, I have to take away that constant term in order to get a Plethystic inverse. So it turns out that the Plethystic inverse is the alternating sum of omega of Li-n. So in terms of Sn characters, this is Li-n tensored with the sign. Okay. Now, of course, Cadogan didn't say this in this way at all. Let's see, so this is a famous formula because a computation of Phil Hamlin combined with a theorem of Richard Stanley showed that omega of Li-n, so Li-n tensored with the sign, is also the Sn character on the top homology of the partition lattice. So you don't need to know anything about all that, but that result basically launched a whole area of research into the partition lattice and its homology. They're Cohen-Macaulay posets, so they have unique non-vanishing homology, and they have very interesting representations. They carry actions of Sn. So that was actually how I first got interested in this. Okay, so as I said, I think I said in the beginning, there are a lot of these Plethystic identities that they seem sort of close, but you can't, if you're looking at it for the first time, you can't quite put your finger on it because suddenly there's an alternating sum, suddenly you're tensoring with the sign. So they're close, but not really close. So here's a meta theorem that, I was trying to understand what was going on. So this is something I came up with. So they all seem to have this general formulation. I'm looking at a symmetric function Fn that looks like this, right? 1 over n, the sum over d dividing n, power sum pd to the n over d, and there's a coefficient of psi of d. So what we've seen so far is the function psi being either the Möbius function or the Euler phi function. But it can be anything, any real valued function on the integers. So this gives you some virtual character of Sn. It actually gives you a virtual character of Sn that's induced from the long cycle.
Sheila, I'm a bit, it's not clear to me what do you mean by raising 1 minus PM to another symmetric function? Oh,
This is not a symmetric function. I'll get to that. Yeah, this is not a symmetric function. Okay.
1 means what? It's a symmetric.
1 means 1, yes, the number 1. So yes, I'll explain it. So Fn of t is this polynomial.
Okay. Yeah, sorry,
Okay?
I jumped the.
Yeah. So Fn of 1 means substitute 1. So I'm taking the sum of all the psi of d's over d dividing n and dividing by n. Okay? So these exponents are actually integers. Okay. So I want to make these little fn's into a series of symmetric functions. And I also want to define what it means to take the alternating sign. I want a notation for it, so I'm going to call it f alt. Right? So this theorem tells you in a uniform way how to compute all these plethisms. So you don't have to do them every single time. So if you're taking H plethism with F, you just take this product of 1 minus PM, this is the mth power sum, and you raise it to the integer power minus Fm of 1. Okay. I can't remember what was on the next slide, but let me just say, if you can see if psi of d is the Möbius function and you plug in 1, you're just adding mu of d as d ranges over all the divisors of n. That's 0 unless n is exactly 1. Right? So this is how you get Thrall's theorem right away, by specializing. Okay.
Sorry, can I ask a question?
And that is what I wrote on the next slide. I'm sorry, yes?
Sorry. So this psi should not be an integer valued function, right? You have written psi goes from n plus to r, but I think, don't you mean n
yes.
plus?
In all my examples, psi is an integer valued function, but for the actual argument, it doesn't have to be.
Okay, because you said this is an integer power, that's why I was confused.
Oh, yes, sorry. Yeah.
Okay.
For the examples that I'm interested in, the examples that I'm interested in, for example, psi of d could be a Ramanujan sum. Right? In those examples, they will always come out to be integers. There's some you can get interesting things. I haven't actually fully explored this, but you know how the generating function for the Catalan numbers has that strange square root in it? So sometimes you can get exponent 1/2 and you can get interesting things there because you're just expanding everything as a formal power series.
Sure. Thanks.
So probably you want the exponents to be at least rational, I guess. Okay. So as I was saying, if you take psi of d to be mu of d, then Fm of 1, this is just the Kronecker delta m1. So it's 1 if m is 1 and 0 otherwise, right? So you immediately get Thrall's theorem and you get Cadogan's theorem because so the value of this theorem is that it gives you all these identities in one shot. So you can pass from one to the other. So you don't have to do individual computations each time. Okay, so Thrall's theorem is actually equivalent to Cadogan's computation. And it's also equivalent to, you can also get results like this. So what am I doing here? So I'm doing something a little bit different. What I end up with is the Plethystic inverse of the Lees, right? And it's the outside factor is the alternating sum of the ENs. Okay, so how do I get that? Let me just say very quickly how I get that. I get that that's a simple observation that I didn't write down. Oh. Okay. No, go away. Right. I'm trying to write. Okay. So what I want to do is I want to point out that the sum of -1 to the n is actually 1 over h. Okay. So if you if you know this and you, here it's just the reciprocal. So what I'm doing, sorry, oh, sorry. Yeah. Okay, so if you just actually take reciprocals of each of these, you can replace H with the alternating sum of the E's, you can replace E with the alternating sum of the H's, and so on, right? So you get a lot of identities that way also. Okay, so that's good. So now we know what the plethystic inverse of the Lees is. It's something fairly simple. I wrote Orlick and Solomon and Lehrs and Solomon, so this is intimately connected with the braid, or the cohomology of the configuration space related to the braid arrangement. So there's a whole area of research there. I won't go into that either. Okay, so I want to do something different. So in the previous slide, I specialized psi to be the Möbius function. Now I want to do something a little bit different, right? I want to take I want to define Kn to be the two valuation of n. So what is this? This is the highest power of 2 that divides n, right? And then I want to take the primitive root, so I'm constructing a new representation of the cyclic group. I want to take that and take its Kn power, right? And I'm going to call that Lie sub n superscript 2. Okay? So the thing to notice is that it's really the same thing as Lie n if n is odd, because there are no powers of 2 in Lie n in that case. And it's the same thing as conj of n if n is a power of 2, because then this power, omega n to the power kn, becomes 1. Right? Okay. So you use the meta theorem and the corresponding specialization of psi of d, right? So you can figure out what that is. Right? You will get this theorem. You will get E of the sum of these Lie n2. So these are actual characters. This is important. Is what 1 over 1 minus P1. It's actually giving you a different decomposition of the regular representation, a new one, at least as far as I know, it's new. It's decomposing the regular representation as a sum of, on the outside, you're tensoring now with the sign. So Poincaré-Grigg-Fit is coming later on, but if you already know about Poincaré-Grigg-Fit, this is strange. It's describing the full tensor algebra as the exterior algebra over something, instead of as the symmetric algebra over something. So I don't know what that means. But anyway, the fact is true. Okay. And then now you can start, playing this game of taking inverses and everything. So the meta theorem gives you this for the inverse of the ENs. Okay. And if you take reciprocals, like I was describing before, you get the plethystic inverse of these funny Lie n2s. You'll get that too, right? So my question is there a more conceptual way to explain it, to actually construct the modules and see what's going on? I mean, all of these, because for Lie, there are lots and lots of places where the particular identity is reflected in either an exact sequence, an acyclic complex, something, right? So that's how those identities were originally discovered in very disparate situations. And here, I don't know anything. I don't know how to explain these identities other than as formal symmetric function computations. Are there any questions? Okay. So I did want to do this one easy computation, but I don't know. I vastly overestimated my time. let's see. So how do you go from Len to Len2? So I want to say the way I stumbled onto this was actually in trying to compute the Plethystic inverse of the sum of the elementary symmetric functions. So I had some god-awful formula and I didn't know what it was. I mean, it was hard to recognize from that formula that these were actually true modules and not just some, virtual representations. So then eventually I figured it all out. So here's the connection between Len and Len superscript 2, right? So as at the level of symmetric functions, this is what it is. It's Len2 and then there's a plethysm with P2. But you can rewrite this in terms of actual modular decompositions in the Grothendieck ring of the symmetric group in terms of Riesz product. So it's actually something that makes sense. All right, so I wanted to go through the proof. So I'm going to leave some little exercises for you to do. The first one is to prove that H plethysm of P1 minus P2 actually gives you E, right? And this is a tremendously useful fact. And also P1 minus P2 and the sum of P2 to the Ks, those are Plethystic inverses. That's not hard to just check by brute force. What did I do? I did something. Okay. So I know I'm using Thrall's theorem, right? So I know that 1 over 1 minus P1 is H plethysm with Lie. And I'm going to freely use the fact that P1 is the plethystic identity and that their plethysm is associative. So in the middle of this, I've stuck in 2 more plethysms because this is just P1. And then I'm rearranging them, right? So I'm going to do H of P1 minus P2 first, and then the powers of P2 to the K with Lie second. The first one becomes E, and the second one is that. So I have a way of writing 1 minus P1 to the minus 1 as plethysm of E and something else. Okay. So, but I already know that it's E of Len of 2. So because I know that E is invertible in the plethystic ring, I can conclude that Len superscript 2 is actually exactly this. So this is pretty much how I got to everything in the end.
I have a question.
Yes.
So the Len has a nice interpretation in terms of GLN modules, right? It's freely
Yes.
algebra. Does Lie2 have a similar interpretation?
I do not know. That is a big question.
Okay.
I have no idea. I don't know. Yeah, that would be nice. It would be nice to figure out what that is, if there is one. Yeah. So I don't know if this is accidental or there is something deeper behind it, right? My feeling is that it's too nice to be accidental, but I don't know.
And then Len has a basis given by Linden words.
Yes.
So it would be nice to have a similar theory for
Yes,
Lie.
it would. Yeah, like I said, I know nothing about Len2 except you could take its definition as, being the plethystic inverse of the E's modulo tensoring with the sign, or you could take the definition that I started with as an induced module from the cyclic subgroup.
So it's definitely sure positive, right? I mean, there's no doubt about that.
Something happened. Whoa. Uh-oh.
Oh, your tablets.
Let's see. Sorry. I don't know what
it seems like your tablet has disconnected.
Yeah. Let's see. Now I have to figure out how to get back. It says I'm connected. Oops. Whoa.
Try sharing again.
Yeah.
But I don't see it. Oh, no, you're there. Yeah, there are two of you. Yeah.
Did it, why is it not? I did the share, but it's not, that's annoying.
I think it's working again.
Is it work? Okay, let's see. All right. Okay.
Yes.
All right, there we go. All right, it's back. I don't know what happened. I don't think I did anything. All right. Okay, I'm sorry. So were you in the middle of saying something? Yeah, all of that is wide open. I don't know at all what Li n superscript 2 is. I would love to know.
Okay.
Okay. Let's see. More specializations, right? So I can take in the psi of d. So I didn't actually write it out because, well, it's the Ramanujan sum. If I take psi of d to be that Ramanujan sum, then I'm really looking at my little fn's, those symmetric functions, are these ln superscript k's, these induced modules. And I get a theorem like this. This is 1 plus the sum of the p lambdas. The sum ranges over partitions of lambda where all the parts are divisors of k. So notice if you put k equals 1, you're going to get Thrall's theorem again, right? Because the right-hand side is going to be p1 and p1 squared and p1 cubed and so on. Okay. What? Oh no. Uh-oh. It's gone again. You know what? Can I? Let's see. I'm going to try. What should I do? Maybe I should try just, I won't be able to write, but I should try just doing it from my laptop. Is that okay?
Yeah, sure. I think that, I mean, yeah, we don't really have a choice now. So.
Yeah. Let's see.
Though it shows another of you, actually.
Yeah, but the sharing seems to be the screen sharing.
Okay.
Why can I not find it? Oh, show all windows. Sorry. Okay. Can you see that?
Yes. Just
let me make it.
Probably the view and then.
Okay, I made it full screen. Is that good?
Yes, yes.
Yes, yeah.
Okay. All right, so let's see what I have to find where I was. Oops. Okay, yeah. All right, so I was here, right? Right, so from this, so I'm just going through some examples of things that you can now get easily. Right? From this, you can get a formula like this, which is, so this is an example of a formula where now you do not have true modules on the right-hand side. I'm taking the actual Lie representation, n over m, and I'm taking Plethism with pm, right? But the sum is over all divisors of the greatest common divisor of n and k, right? And it just confirms the fact that these representations depend only on the greatest common divisor of n and k. That's one thing that you get out of those Ramanujan sums. Okay. All right, so here's, Amri, how much time do I have? I'm just looking at my clock here. Sorry.
Yeah, I mean, we often finish late, so it's not such a big deal. But you could take 10 or 15 minutes more if you like.
Oh, okay.
I mean,
Sorry.
I guess if people are busy, they can
Yeah.
leave. But as has also been a suggestion from Anna that we could have one more talk and go into things a bit more in a leisurely way. I think that would be nice next week.
Okay, let me think about that.
Yeah, we'll think about that later. So, but
Yeah.
let's keep that as an option.
Okay. So I'll just do this very quickly then. Let's see. So this was the thing that you had asked me about, right? So this is new. Wait, I think I skipped a slide. Ah, there we go. Okay, so Richard Stanley had conjectured that the Plethystic inverse of the oddly representations is this strange looking symmetric function. So what are we doing? We're taking the sum of the odd e's on top and dividing by the sum of the even e's, right? So, why you would think that's going to come out to be nice is, beyond me, but this is Richard. So the way he conjectured this is by taking what he called the exponential specialization. It's in the EC2, right? And then you get a nice, just in terms of ordinary generating functions, you get a nice formula, compositional inverse formula. Okay, so this is, you'll see what the compositional inverse formula is, right? So the theorem is, so I was able to prove this theorem, right? And then the corollary that well, it's not actually a corollary, it's a separate computation. Then you get, if delta n is this shape, so this is the staircase shape, right? Then what this expression actually is this alternating sum of skew shapes. And it's also this hyperbolic tangent of the sum of hyperbolic arctangents of xi's, right? So again, going back to my childhood, when I also really liked trigonometry and things. So this was all very exciting. All of a sudden, wow, there's trigonometry in here. Yeah, so this, I could prove this, but this has a history. So there's something very similar that had already been known. And that is this result. So from that previous result, I was also able to prove what the Plethystic inverse of the alternating sum of the odd Lees is. So it's actually, you just put the signs in the obvious right places and it somehow miraculously works. Right? So this function has been studied before. Right? There's actually quite a lot of literature on it. It goes back to Karlitz. There's a 1973 paper of Karlitz, and he shows these two things. It wasn't so obvious to me how to get these two facts, but I think it's all in there. So this is actually a sure positive function now. So this is, in fact, a true representation of Sn. So it's the sum of skew Schur functions, and it also happens to satisfy this tangent identity. That's not hard to show. Okay. So again, so the two new identities are the Plethystic inverse of the odd Lees and the Plethystic inverse of the alternating odd Lees. Right? And what that gave me was, so I was surprised. Sometimes I feel like I fall over decompositions of the regular representation no matter what I do. Here's another one. If you take hk subscript n to be the sum of all the irreducibles indexed by hooks, one for each one, right? Hook shapes. Then the regular representation decomposes as the sum of all those hooks, Lethism with the odd Lie representation. And I have no idea why this is happening. So if you put this in the GLV context, hooks show up in the exterior power of the natural, the defining representation. So maybe there's something going on there. I actually don't know. Okay, so remember, yes, somebody had a question? I'm just going to end with this, actually. Okay, so in those two theorems about the oddly representation and the oddly representation alternating with the signs are actually an example of a more general phenomenon. You know, I wanted to figure out why that worked. So here's the theorem. So if you fix a k and you take a sum of symmetric functions of homogeneous degree, this is congruent to 1 mod k. Right? And so I'm taking two series of symmetric functions that are congruent, where the degrees are congruent to 1 mod k. And I do the alternating sum on each of those. Then the theorem is that if these two are Plethystic inverses, then the alternating versions also have to be Plethystic inverses. So that was a little tricky to prove, but now it's good. I'm glad I have it, because that explains what was going on there. So again, from this you can get, you know, lots of other examples of, you can go from one Plethystic identity to another. Okay, so maybe I should stop. The slides that follow are sort of, maybe here, let me just, okay. I was going to put everything in more properly in the GLM context, right? But I think I should probably stop.
Well, there seems to be a popular demand for one more talk on this, so that we can really go through things. So maybe we'll discuss that.
Okay, yeah. So I just wanted to, yeah, there was a, yeah, I had some reference. Well, the slide, you now have the slides. I had a list of open problems that
Right.
are probably all very hard, because people have tried this for a long time. And I was going to say something about characters. Oh, yeah. And then, yes. And I was going to write on this slide, and now I can't. So I'm very disappointed. I was actually going to write in Tamil.
Oh, no. Okay. So, well, no, that was great, but thank you. Thank you very much. Let's
Thank you. I'm happy to answer questions. Maybe
Yeah.
try and more
So
questions. I don't know.
questions, just unmute yourself and ask.
You can hear me, right?
Yes.
So can I ask a question?
Yes.
So you had this Plethystic formula in terms of the sums of oddlies, but you did not have a formula for this Plethystic inverse for this alternating sum of oddlies.
So wait, sum of what? I'm sorry.
Odd Lie sub
Yes.
odd fellows?
Yeah.
So, but you did not seem to have a formula for the alternating sum of odd Lie fellows.
Oh, I do.
Oh,
Yeah.
oh. But
Sorry, let me go back.
Regardless.
Sorry. No, I meant yeah, no. I meant the decomposition of the regular representation. So the next slide.
Yes. Yes.
This one. Yeah.
Correct.
So
So this is very specific. It says so the outside factor is the hooks.
yes.
So I'm taking, so this actually has, these are actual modules, right?
Right.
So I'm taking, if you wrote this out in terms of, all right, so in terms of GLN modules, what am I doing? I'm taking the odd generators of the Freely algebra, right? I'm just taking the subalgebra generated by the odd degree terms. And then I'm taking I'm composing with these hook representations. So for GLN, the hooks come up when you take the exterior power, the exterior algebra over, so if it's GLV, it would be the exterior algebra over V, right? So the kth exterior power decomposes as a sum of two hooks. I'm trying to do this in my head, okay? So you can sort of, you can sort of picture this that way. That's what's going on. You're composing two GLV representations.
But there's no analog, a hope for an analog for an alternating, for replacing.
Well, if you alternated here, first of all, you would immediately get something in the growth and decreasing, right?
Yeah.
So then it wouldn't be, I highly doubt it would be the regular representation anymore, but I haven't thought about it at all.
No.
But maybe you get some kind of interesting, I'm sorry?
Sorry, but I just meant, could you replace also the hooks by something else so that you get regular?
Yeah, you probably could. Let me see, I'm trying to think about it. Yeah, I don't know. I haven't thought about it. That's a good question. I'll think about it.
Thanks.
Yeah,
Nice question. Thanks.
You know, I don't know, because a lot of times, like I said, you do this, you know, souped up 10-year-old algebra and you get these strange things, and you really want affirmation that they're interesting from some other context.
So I have a comment.
Yes.
And it's, well, you'd mentioned that there's nothing on the side of GLN that corresponds to tensoring with the sign character in representations of SN. So in fact, I had asked the same question to Shraddha a few years ago. What is it on the side of GLN representations that takes the place of tensoring with the sign character? And it turns out there is actually a functor. It's called causality. And it was defined in a very abstract way by Henning Krause. And Shraddha and I sort of brought it down to the level of Schur algebras.
I'd be interested in seeing that.
Yeah, so
Yeah.
I'll send you something about that.
Okay.
But it's, yeah, and so then we have a slightly more combinatorial approach to it, but we haven't really worked with it too much in that context.
I see. Okay. Yeah.
Are there any more questions? Okay, yeah, I certainly need more time to absorb a lot of, it's just beautiful. There's so much to play with here. So
I'm glad you found it interesting.
Yeah, it was just timely as well for us. So thanks a lot, Sheila.
My pleasure. Thank you. Thank you very much for having me. Are there questions in the
A couple
chat?
of comments here.
I actually didn't look at the chat at all, so.
Yeah, so there were demands for another talk.
Okay.
Actually, Anna had to give 2 talks because she also had more slides than.
Yeah. Thank you. Yeah. Yeah, just, you know, send me an email or something if you have more questions, and I will try to answer them.
Yeah, and I still don't have a speaker for next week, so we could think about, if I mean, I don't want to force you or anything, but if you feel comfortable with it, we could think about.
It's just, I think I would have to. Okay, yeah, let me think about it, because I think I'd have to make more. Maybe I can do the examples that I didn't get to do or something, if you would like to see that.
Yeah, let me go over this, and I'll yeah, we'll discuss it by email.
Well, excuse me, can I ask a question?
Oh yes, of course, please.
Yeah. So you define something about like Lee with superscript 2, right? Like, why do you come up with that thing.
I'm sorry, I didn't.
So you define like D and with a superscript 2, right?
Yes.
Like I mean, because the definition looks very strange to me. Like, why do you come up with like
Oh,
two
what was the
valuation?
motivation? Yeah, I was
Yeah.
trying to explain that. Let's see. How do I go back? Let me go back. This can actually be okay, there. Yeah. So yeah, I did try to explain that. So what I wanted to do was, so we know we have the Plethystic inverse for the H's, the sum of the H's, right? So I thought,
Yeah.
what's the inverse for the E's? Like, it's a natural, obvious question, right? And nobody seemed to know, so I started calculating it, and I got an expression for it that I couldn't recognize. You know, I hadn't done a lot of this stuff in a while, so I didn't know what it was. So then in trying to understand what it was, eventually I figured out that this is what it was. Okay,
I see.
so this can actually be generalized. The two valuation, I think I saw Vasu in the chat. So Vasu's heard me speak about this before, I think. So instead of 2, you can replace it with any prime. You can actually replace, you can do a whole set of primes. Okay, so this was, there's an extended abstract from 2 years ago, and it's also on arXiv. There's an extended abstract on the FTSAC website from 2 years ago. But it's all on arXiv, and I'm happy to point you to it.
Yeah.
Yeah. So that's how I came up with it. It was really serendipity, not brilliant insight, just accident.
And also another things like so there's a theorem that says like the Plethystic inverse of the sum of all the 2n minus 1, right? You come up with this. But like why? So like the term are all odd. Like what happens if it's like even?
What happens? Oh, you're talking about this one?
Yeah, like there's
okay.
like all
so
odd
if you
terms,
take the
right?
even ones, it's so remember the theorem I wrote down at the beginning about what will guarantee that a Plethystic inverse exists. So your series has to start with P1, right?
Yeah.
So you can say something about Plethysm of H with even Lees, something nice comes out of that, but you won't get a Plethystic inverse result unless you threw in the P1. But then, so if you went P1 plus Lee 2 plus Lee 4, maybe you'll get something nice. I don't know. I haven't looked at that yet.
Thank you.
Pleasure.